Hi class, welcome to week 11 of Wk11 Global Climate Change. This week we'll be learning about the last glacial maximum, so glaciation, and the following deglaciation, bringing us into our current interglacial period. So the lab that was going to be due this week, Lab 9, is going to be merged with Lab 10, which is due the following week on April 27th, because if you recall in the schedule, they were originally split into two different parts. So I decided to merge them into one, and so this one lab will be due on April 27th. This way, you can focus on the 3 chapters of content that we're going through this week. So in your Ruddiman textbook, that would be chapter 13, which is glaciation, chapter 14 on deglaciation, and chapter 15 on millennial scale oscillations and climate. So that's a lot to go through. Our self-test will be posted tomorrow on that content, and it'll be due a week from Sunday on April 22nd by midnight. So please read the material carefully and go through the videos I posted and try to respond to the prompts I gave in the forum. It should really help you out with the self-test. In addition, this week, we also have the next milestone of our paleoclimate proxy project due, and that is the outline for your lesson. Now, keep in mind that these lessons are meant to be 15 to 20 minutes in length. So instead of giving lots and lots and lots of content and information, try to focus on your main goal for your lesson and how to convey that material as clearly as possible. So for that milestone due by midnight on Friday, the 20th of April, I want you to give me just a sentence stating your objective, what do you want to accomplish with your lesson, and a brief overview of how you are going to accomplish that and what medium or media you're going to use. Is it going to be video? Is it going to be something that you write up that we have to read? Like, how are you going to portray this lesson? And you can be as creative as possible as long as it's something that you can share via a link or links on Moodle with the class so that others can watch and learn from it, because we're all going to respond to each other's videos, okay? Now, so back to the stuff for this week. The last glacial maximum was 21,000 years ago. So the Laurentide ice sheet was the biggest ice sheet on the globe, and it was covering Canada and the northern part of the US. That means in Greenfield, we would have been under over a mile of ice. So Greenfield was completely covered. And then, due to Milankovitch cycles, so remember these are orbital scale controls on insolation, once again, so the strength of the sun. So the sun was on a precessional period interval where the northern hemisphere was tilted toward the sun during perihelion, and perihelion, recall, is when the Earth's in its orbit about the sun. It's when it's closest to the sun. So this means that 10,000 years ago, we were at an insolation maximum during northern hemisphere summer. And northern hemisphere has a lot of land. And land has a smaller heat capacity than water, meaning it's more sensitive to changes in temperature. Whereas in the southern hemisphere, there's more water than land, so it's less sensitive to these changes in temperature or these changes in insolation. And that drastically influences the global oceanic atmospheric circulation. And so we had intense global warming 10,000 years ago due to orbital scale controls on insolation. Now, during the last glacial maximum, there was a large volume of water held in ice sheets on the continents. So that means we got a sizable drop in sea level. And so when the glaciers started to retreat, and by retreat, I don't mean that they technically traveled northward, it's that their lowest extents traveled northward. So they melted, right? So the meltwater is moving southward while the glacial extent keeps getting pushed back further and further northward. And so when these glaciers melt, sea level is going to rise back up. And now, in order to approximate what climate looked like at this time, so temperature and precipitation, what this looked like at different areas on Earth throughout this time, we combine many different types of paleoclimate proxies now. And so you're getting to see how these proxies are applied. So we're looking at plankton, we're looking at forams, we're looking at sediment, tree rings. So we're combining all these different types of indices now to infer what the climate looked like on Earth over these times. And so another thing I want you to think about is that water is powerful. It's really strong, especially when it's meltwater coming off of a glacier. So if you need to, rewatch the video from week 7 on how do glaciers shape the landscape, because much of our surrounding landscape up here in the Northeast was actually molded by the glacier retreat. The Great Lakes were made by the glacier retreat, the Finger Lakes, and even when the glaciers drained here, the water filled the Connecticut River Valley, which the base of it eventually gave way to draining what was once glacial Lake Hitchcock, and that drained into the Long Island Sound, and what was left behind is our Connecticut River now. So I have a link with a little more information about glacial Lake Hitchcock posted if you want to go through that. And I want you to think about how these retreating glaciers carved out the area we live in today. And so there's also a video posted on how glaciers shaped the Northeast. Go through that as well. And also, when these glaciers melted, it wasn't some constant rate of melt. There was a lot going on there. So when we had warming, and the retreat began about 20,000 years ago. So when we started to get global warming again, we had accumulation of greenhouse gases in the atmosphere. And so that caused a warming feedback. And also, as the glaciers melted, right, ice has a really high reflectivity. It has a high albedo. So as the ice melted, it leaves behind land and ocean, which have a much lower reflectivity or albedo. So they absorb more heat or energy from the sun, and they kind of propagate the process of melting, right? They feed back into it, making this process move faster. Well, along with that, glaciers still weren't melting at this consistent rate. So about 13,000 years ago, we had a brief cooling period embedded in that warm period. So this brief cooling period was called the Younger Dryas, and that went from 13,000 to about 11,500 years ago. And so during this time, the melt slowed a little bit. All right, and we have evidence for this in the form of pollen and in the form of coccoliths and forams. And speaking of coccoliths, so these are shells of coccolithophores, and they're made of calcium carbonate, which is really sensitive to changes in temperature. And so we can look at the ratio of organic compounds in these shells to infer what the sea surface temperature looked like. So I have another video posted so that you can see what a diagram of a coccolithophore looks like and learn a little bit about it that way, so that you're more familiar, so that you can visualize it a bit better as you're reading more about it. And finally, we're going to end this week looking at millennial scale oscillations of climate. Now, millennial scale means pretty rapid in the scheme of geologic history. So we're looking at tens of years to thousands of years of these brief, really quick changes in climate. And we tend to see these oscillations during glacial periods, but not as much during interglacial periods. So I'm going to also annotate several figures from your textbook and post my descriptions on Moodle, go through the key terms for the week, and you'll see in those key terms that not all of them are bolded in your textbook chapters. That's because some of these terms we've gone through earlier in the semester, such as freeze-thaw weathering, which is really important during glacial intervals, right? Because when glaciers, ice sheets melt, so the water fills in cracks in the rocks, and then when that water refreezes, water expands. The solid phase of water is less dense than the liquid phase, so it expands, and then that expands and joints the rock and splits it apart, and so that is a form of weathering, right? So it breaks it apart. And glaciers, when they transport rock and rock fragments, it works in this really interesting way in that it carries these materials like a conveyor belt would carry materials. So there'd be rocks on top or sometimes embedded within the ice sheet, and it carries it with it because ice is a fluid and it flows slowly, but it does flow. Okay, finally, go through the concepts, the bulleted concepts that I outlined for you. Those are the main points of these chapters that I really want you to think about. And so please feel free to elaborate on those in the forum and to also try to annotate some figures on your own to practice for the self-test. So I hope you enjoyed learning about glaciation and deglaciation, and I will see you next week.